Welcome back to another episode of Folzor, and in this, we're going to talk about this JK flip-flop. And let me tell you something real quick before we go any further. This took me forever to make. I have so many iterations of failed JK flip-flops, and I mean, if you're a true fan of mine, you'll see that about a week ago, I posted a video about how to make a JK flip-flop from transistors, and that circuit was so bad. It was so bad. It was hard to get output from it, and it wasn't terribly reliable, but it did work like 85% of the time, 80% of the time, but not really 100. So it's hard to make that into a computer, but I finally developed the technology properly, you can say. It takes 22 transistors to make a reliable single JK flip-flop. So also, if you watch the how to make a computer series, I said I'll see if I can pull up the clip, but I said, oh, a JK flip-flop will only take 6 transistors and we can use a capacitor to make a clock pulse. No. And then the JK flip-flop right here is going to use 14. I mean, yes, you can. You can't really do it on a breadboard because since the pins are so close to each other on the breadboard, they kind of act like a mini capacitor. And since the capacitance we would use on a capacitor is so small, it really just would not work. On a breadboard, maybe on the little soldering boards I have, we could get it to work. But I was like, nah. I mean, we're just going with the master slave technique, and I'll explain this, and I'm gonna explain all of the failed circuits that I did too in this video. So this is the circuit for the JK flip-flop, and I do want to clarify that these two circuits, this one and this one, they're identical. This one's just on a breadboard, so hopefully it's a little easier to see and kind of understand. Let's turn this voltage up. There we go. So I don't have a button for it because I'm kind of like stupid. But if we put this resistor in, hopefully we can trigger it on. There we go. It's a latch. And then, yeah. So yeah, I mean, it does work. A little wonky. It works better on the actual soldered PCB board, you could say. But this is a master slave JK flip-flop using only 4.7 kilo ohm resistors and 68 kilo ohm resistors. Okay, guys, I mean, I just spent the last 3 hours of my life trying to hook up this circuit, and I kind of got it right, but not really, because all the outputs are inverse, so I'll still have to go figure it out. But right now they do toggle in sequence, so I guess that's a little bit of progress. But let's look at this JK flip-flop with these 3 outputs. So if it's off, it's considered on. So we have 1, 2, 3. See? So it does work. It does do it like a full cycle, I guess you can say. I guess it kind of counts backwards, which, I mean, all we need really is a program counter. So I guess this would still be sufficient. It would just be not standard, which kind of bugs me, but I mean, it is what it is at this point. Transistor computer is freaking hard, bro. It is hard. But yeah, this is where the progress is towards the computer. It's really all I have to say about this. It is cool though. It's pretty reliable, which is also something that I value very highly, because we don't want to skip programs not at our will, because that's how AI takes over the world, and we don't want that to happen. We don't want to contribute to this destruction of our society. So, but that's it with the JK flip-flop. So this is the exact circuit that I made. And so let's look. It's a master slave JK flip-flop. We do not use the capacitor. like I said in previous videos, because I'm an idiot, and it turns out that way it's not too reliable. So let's look at this. So right here we have these 4 NAND gates, right? So you can make a JK flip-flop master slave with 4 NAND gates. And this is a JK flip-flop, you could say, without the J or the K. So it's just a flip-flop. So every clock pulse it flips and flops. Just so we get this kind of binary counter thing. Since we don't need the JK function, I just straight up didn't add it in. So every clock pulse we swap. And it's made using these 4 NAND gates. I'll put a little image up from the simulation of how we made it. So these NAND gates connect like that. The output goes into the input of this one, and then the input goes into the output of one goes into the input of the other, kind of so we can save the state. And then we do the exact same configuration on the other side, and we had this little NOT gate that inverts the clock signal. So when we store one in this one, we kind of shut off the other one until we release the button. So if you want to like pause the video, slow it down, kind of really see how it works with every clock pulse, or you can make it on your own, you can. I mean, I can't stop you really, so you can do whatever you want. But that is how the main circuit works. We have the 68K on these buffers right here. And these buffers, their main purpose is really to re-amplify the current again, since this current right here is not really that big. It's kind of small, so we need to like re-amplify it again. So we have 2 NOT gates to make one single like buffer, and then we go and do the same thing over here. And that's how it works. We have what 2, 4, 8, 8 plus 8, 16, 16 plus another 8, right? 24, right? 24, 16. Yeah, 24 transistors, and probably about 24 looking resistors too. So it's kind of a hefty little circuit, but we need it. We do need it for the this operation to work successfully. So now let's look at all of the failed attempts, because I mean, I'm gonna be straight up clear with y'all. They deserve some attention too, because I spent hours on these circuits. So I'm gonna share with you all of my failed attempts too. So let's go into the files. We're gonna say this real quick. Now, if we open the files, I mean, I can't really see it, but my naming scheme for these circuits is JK, better JK, better JK, and then best JK. So I don't know if y'all name y'all stuff like that too, but I don't rename it to what it is. I just put better in front of the words, and I do the same thing with 3D modeling too. Okay, so this is an old one. Oh, so this is actually the one that I made in the last week's video in the simulation. But it's so hard to get like an output out of this, and I kind of did with this one, and it works. I mean, this JK flip-flop works really well in the simulation. But I mean, notice I have a 5 ohm resistor, so I mean the current running through this transistor right here is just like stupid high. And then right here I had this little way where we can kind of force what state we want it in, so we can make a good little like jump command. But it's like I said, this is really hard to actually implicate or whatever in real life, but it does work in the simulation. And I mean, look, if you want to take a second to screenshot this, and if you can get this to work, then please let me know, because it took me forever really to make this attempt at making the circuit work well in real life. It took me a long time. Now let's go into the other JK flip-flops. Oh yeah. So this is actually a long chain of JK flip-flops, and we do something very similar as the one that we are implementing, the best one. We do use like this little NAND gate technique, and we do have the clock signal with the capacitor. But this one's really complicated, and I didn't actually want to make this in real life, but it does work. At least it works well in the simulation. And I got outputs from it, but I never really attempted this in real life just yet, because I mean, just kind of look at it. It looks a little complicated. So again, and plus it uses a lot of current. I mean, it is three of them at one time, but and this is the other one I attempted. So a JK flip flop is kind of just like a latch button, you could say. So if you look up latch button circuits, that's really just a fancy JK flip flop. So I went down that rabbit hole for a little bit and tried to make a whole bunch of these latch circuits like this, and I really could not get a good output. I mean, you can see like every now and then it's gonna latch, and we can continue the circuit, but again, it's just so unreliable and so impractical. This is another attempt of me doing it too, just with a latch circuit. Most of them like call for MOSFETs, but I don't have that many MOSFETs lying around, and I don't really want to buy them. So we just went with the OG Master Slave JK flip flop design, and that is what we are going to be rolling with. So, um, yeah, and that's it. We're gonna have three of them, so we're gonna have 16 bits of program counting that we can do at maximum, and I think that's all we really need for our little computer. Um, yeah, I can't think of anything else. I mean, that's it for this video. If you learned something, you know, drop a like, drop a comment. If you like electronics, please subscribe so we can grow this a little faster. Um, but yeah, I mean the transistor computer is being made right now, so hopefully we'll have that done by the end of the year. But thank you for watching. Okay, yeah, I lied in that last part. This is not the end of this video. This will be the last little segment of it. But I mean, dude, like, look at this right here. We got a little A-stable multi vibrator, and then it's hooked directly up to the JK flip flop. So now the clock can control the JK flip flop output directly. I mean, dude, like, what is more we can ask for in the progress towards making a computer besides this? I mean, there's nothing better than watching this. So, just want to share this progress with you. We will review how to make a little clock, an A-stable multi-vibrator, which is the black thing right here. But, I mean, I just got to share this carousel of progress with y'all.